Welcome back. I have a tank here, and inside this tank I have a liquid that has the density of 900 kilograms per cube meter. So it's not water, it's another type of liquid, and it has different density, 900 kilograms per cube meter. So this is the tank's cross section. It's an ellipse, and the equation of this ellipse is 4y squared plus x squared equals 1. That's the equation for this ellipse. That is the cross section of this tank. And now your task is to determine the resultant force that the liquid inside the tank exerts on this elliptical end plate. So you first need to find the total force that this elliptical end plate experiences. And then you need to find the center of pressure through which that force acts with respect to the origin of this coordinate frame here. The assumption is that the tank is completely full. So try it out by yourself first. In this case, also use an online integral calculator. Don't try to do it by hand. And so once you're done, you can see the solutions in the next video. Thank you very much. Welcome back. So let's now find the resultant force and the Cp for this elliptical end plate. The density of the liquid is 900 kilograms per cube meter. The tank is completely full. Now this is the side view of the tank. You're looking at it from the side. And this side here, that's the elliptical end plate. It's this one, but looking from the side. You can see its pressure distribution from inside the tank. But now, what is different is that this time, the elliptical end plate has variable width, and it needs to be taken into account when you calculate the resultant force and the center of pressure. You can see that here you have one width, here you have another width, then here you have another width, and then here you have another width. So that needs to be considered. Now the pressure here equals, like always, the density times G times Z. And we assume that Z is positive as you go down. So from here on the top, when you go down, your Z increases. And now you know your density, it's 900, and then you multiply it by G and Z. That's your pressure function. And now, looking at this end plate from the top, what we can do, we can define an infinitesimally narrow strip here that experiences some kind of pressure at the depth Z. So this is the infinitesimal width, dz. Then this strip has a length, let's call it L, as a function of Z, because it depends on your Z. It's different when your Z is different. And now, the infinitesimal area of this strip, dA, it's L as a function of Z times dz. So it's this infinitesimal area. And remember, this narrow strip, it experiences some kind of pressure. Therefore, the differential force exerted on this strip is the pressure as a function of Z at this specific Z for this specific strip times dA. So you take your dA, you multiply it by the pressure, and you get your differential force. In other words, you can rewrite this equation like this. P as a function of Z, and instead of dA, you write L as a function of Z times dz. And you know your pressure function. It's this one, 900 times G times Z. So I'm going to write here 900 times G times Z times L as a function of Z times dz. And now we need to find how this L as a function of z changes with z. We need to find a function for it. We know that this end plate here, it's an ellipse, and if we have an xy coordinate frame in the middle of the ellipse, then this ellipse is described with this equation. Now I will rearrange this equation like this. X squared equals 1 minus 4 times y squared. Or in other words, x equals plus minus and then square root of 1 minus 4 times y squared. So we have x as a function of y, and we have two functions. We have x equals and the square root of all this, and x equals minus square root of all this. Now the first equation, it can be graphed like this. So you have the part of the ellipse on the right side, and then the second equation, it can be graphed like this, where the part of the ellipse is on the left side. But now, what I want is y as a function of z. So remember, in both cases, positive z goes down from the top of the ellipse. And so we want to relate y with z. You can see that z starts at when y equals 0.5 meters and positive z is down. That means that y equals minus z plus 0.5. You can see that when z equals 0.5, then y equals minus 0.5 plus 0.5, which is 0. Then when z equals 0 meters, then y equals 0 plus 0.5, and that's 0.5 meters. And then when z equals 1, then y equals minus 1 plus 0.5, and that's minus 0.5 meters. That means that I can rewrite my x's like this. X equals plus minus, and now square root of 1 minus 4 times, and now I simply replace the y with minus z plus 0.5. So minus z plus 0.5, and then I have to square it because I have y squared here, and so all that is under the square root. So now what we have is x as a function of z. But what is L here? What is L as a function of z? Well, L as a function of z equals 2 times the absolute value of x. Or in other words, 2 times the absolute value of x as a function of z. For each given z, you have some kind of x, and L is twice of that x. You see, you have x here, and then you have the same distance here on the other side. Now the reason why I put the absolute sign there is because I don't really care about the signs for L. I just want the magnitude of L as a function of z. And for that, I only need the magnitude of x as well. So even though here on the left side you would have minus x, but to get the total length of L, this minus sign is unimportant here. And so I can say that my L as a function of z, it equals 2 times square root of 1 minus, and then 4 times, and then minus z plus 0.5, and then you square it. You can check if it's correct. L at z equals 0, that's 2 times, and then all this, and that gives you 0 meters. So when you're up here, then obviously there is no length. Then L at z equals 0.5 meters, that equals 2 times, and then all this, and that will give you 2 meters. So when z equals 0.5 meters, then you're here. You're right in the middle of the ellipse. And you can see that you have 1 meter here and 1 meter here. And so in total, the length is 2 meters. And then finally, when you have L at Z equals 1 meter, then you have 2 times, and then all this, and then again you have 0 meters, which makes sense, because when you are down here, then you have no length. But that's when you have Z at 1 meter, because you start from here, and then as you go down, once you reach here, your Z equals 1 meter. 0.5 plus 0.5, you have 1 meter. And now that we have L as a function of Z, we can take this df function, which in the end was this entire thing, and now we know what our L as a function of Z is, so I will have df equals 900 times G times Z, and now instead of L as a function of Z, I will have 2 times, and then all this, and times dz. Now remember, this G here is 9.81 meters per second squared. And now if I integrate it, and then on this side, I perform an integration from Z equals 0 meters till Z equals 1 meter, well then I will get the total force that this elliptical plate is experiencing due to that liquid inside the tank. If I evaluate this integral, then I will get 6934 times 28 newtons. I found it using Wolfram Alpha online calculator. But now we also have to find the center of pressure through which this force goes. We know one thing. Due to symmetry, the center of pressure is somewhere on the y-axis at x equals 0 meters. That's because you have equal distribution of pressure on both sides of the y-axis. But of course, the question is, where exactly on the y-axis you have that center of pressure? For that, I will compute the total moment about Z equals 0 meters due to this pressure distribution. So you have your pressure distribution here, and we're going to calculate the moment about this point, which is Z equals 0 meters. So I'm going to call it M about Z0. And now remember, you have your differential force here that corresponds to this narrow strip. And now if you take this df and you multiply it by its moment arm, which is Z, so Z times df, and you integrate that, meaning that you do the same thing for all the infinitesimal narrow strips that you have on this ellipse, well then you will get the total moment about Z equals 0 meters. Because remember, Z times df, that would give you a differential moment. So I can also write it here. dmz0 equals Z times df, and that's for this infinitesimally narrow strip. And then you have to do the same thing for all the narrow strips. Take their df, multiply by their corresponding Z, and then you add up all these products. So you integrate this equation. That will give you the integral from Z equals 0 meters till Z equals 1 meter, and then you have Z times, and now instead of df, you have all this, and if you evaluate this integral, then you will have this result, 4333.93 Newton meters. Again, I used Wolfram Alpha online integral calculator for that. And now, if I take my total force and I multiply it by the Z bar, which is the center of pressure But in terms of this z variable, then you need to get your mz0. And so that means that your z bar equals mz0 over f. You have your mz0, you have your f, and you get 0.625 meters. And that's the center of pressure of the liquid applied on this elliptical end plate. However, since y equals minus z plus 0.5, then instead of z, I will have z bar here. And so that means that y equals minus 0.625 plus 0.5, and it's minus 0.125 meters. And so if I have z bar here, then actually this one is my y bar, and also this one is my y bar. And there you go, you know your center of pressure. Your force, it goes through the center of pressure of x equals 0 meters. In fact, it's x bar equals 0 meters, and y bar equals minus 0.125 meters. So it's somewhere here. And in this image, it's somewhere here. It's at x equals 0 meters, but it has a negative y center of pressure. And it makes sense that your center of pressure is here, because this is your distribution here. And so with this triangular distribution, it has to be below the origin a little bit. So that's how you deal with fluid pressure when the plate has variable length. Thank you very much. Welcome back. I have an underwater tunnel here, which is semicircular. The total depth from the surface of the water till the bottom is 9 meters, and the width of the tunnel is 6 meters. The bottom of the sea is flat. It means that the depth of the tunnel stays 9 meters always as you go along the length of the tunnel. The density of water is 1,000 kilograms per cube meter. And now the question is, what's the resultant force per unit length along the tunnel? And what I mean by resultant force per unit length, it's this one. It's WR in newtons over meter. So I'm not looking for a specific point force because I don't know how long this tunnel is, but that's okay, I don't need that. I need the resultant force per unit length along the tunnel. Now what you can see is that this tunnel experiences pressure due to water, and its magnitude and direction changes with depth because the tunnel is semicircular and the pressure is always normal to the surface. And of course, in this image, the pressure is in pascals. One thing is clear, the center of pressure per unit length will be located along the length of the tunnel on the highest point of the semicircle. So WR will run along this line here. So in this image, it will be positioned here, and then it will run into the screen. And that's, of course, due to symmetry about this vertical axis. You can see that all the horizontal components of the pressure distribution in this image get cancelled from the same horizontal component from the other side of the semicircle. So you can see that this one here gets cancelled by this one here. So you don't have to worry about the horizontal components here. And then all the vertical components point down, and due to symmetry, all the vertical components of the pressure distribution are the same on both sides of the semicircle. So this one here is the same like this one here. And then of course, At the very top, here you only have one vertical component, and then here you only have the horizontal component that is cancelled by this horizontal component here. That's why this WR must run along the line on the top of the semicircle. In order to find WR, you could use the traditional way, the integration. Let's define the variable C that runs along the circumference of the tunnel. You know that the width of the tunnel is 6 meters. It means that its radius equals 3 meters. Now the circumference of the total circle from here till here, it's 2 pi r meters, r being the radius of the circle. So the total circumference of the semicircle, it's pi r meters. Because of the fact that the curvature of the tunnel constantly changes, the magnitude and the direction of the pressure distribution also constantly changes. In that case, the distribution per unit length will be a vector that in general has two directions, WRX and WRY. Note that this is how I defined them at the beginning. Of course, in the end you will find out that this will be 0 because the horizontal components, they cancel each other out, and WRY, it will actually point down. But as a general case, let's first define them like this. And so you have to get both of them. And now here's the thing. At any given circumference, you have a differential DC, differential circumference, and it experiences pressure as a function of C, as a function of circumference, and this pressure as a function of C, it has two components, the X component and the Y component. And now we can say that this DC, it's at an angle theta, and since this red vector, P as a function of C, since it's perpendicular to DC, this angle here, it's also theta. And it makes sense, because if this theta angle here is 0 degrees, so your radius is like this, then also this angle theta would become 0 degrees. And if this theta angle becomes 90 degrees, so the radius is like this, then also this angle here, this theta, it becomes 90 degrees. So this theta is the same like this theta here. And so we can say that P as a function of Cx equals P as a function of C times cosine theta. And then P as a function of C, Y equals P as a function of C times sine theta. And now here's the thing. Both of them are in newtons per meter squared. And then DC, well, it's simply in meters. That means that if I say that the X component of the pressure is multiplied by DC, then you will get newtons per meter squared times meters, and you will be left with newtons over meter, which means that this thing will equal differential WR in the X direction. And the same thing with dWRY, the differential force per unit length in the Y direction, it will be the pressure in the Y direction times DC. But you already know that this thing can be written like this, and this thing, it can be written like this. However, notice now something. If this is your radius, and this is your theta, then this C here, it's your arc length. You can say that C equals R times theta. because that's how you calculate the arc length. If you have your radius and your theta, then your arc length equals r times theta. But that also means that if I now say that I have here d theta, so it's a differential angle, then I can say that my dc, my differential circumference or differential arc length, it equals r times d theta. And so if before my dw rx was this expression, in other words, the pressure as a function of the arc length times cosine theta times dc, then now, since I know that my c equals r times theta and dc equals r times d theta, in this function, whenever I have a variable c, I can replace it with r times theta, and then dc, it will be r times d theta. Then here I can easily say that I have pressure as a function of theta because I simply replace every arc length that I have in this function with r times theta. And r is a constant value, so I don't have to include it here. So it's just a notation. If I know that whatever function I have in my p as a function of c, if I know that in that function every single c is replaced by r times theta and r itself is constant, then instead of p as a function of c, I can say that it's p as a function of theta. And so that means that this expression here, I'm going to rewrite it like this. Pressure as a function of theta times cosine theta, and now times r times d theta. And the same thing with differential wry. First I have pressure as a function of arc length times sine theta times dc, but then since all my arc lengths will be replaced by r times theta, then I'm just going to say that pressure as a function of theta times sine theta times r d theta, it equals my differential force per unit length in the y direction. And now, using these two functions and using everything else that you have learned so far, your task is to find the total wrx and the total wry. Now you already know that this will be 0, but I would like you to convince yourself by getting this 0 mathematically. So find this one and this one. Try it out by yourself first and then see the solutions in the next video. Thank you very much. Welcome back. So let's now find wrx and wry. We know that the depth of the bottom of the sea is 9 meters. We also know that the tunnel's radius is 3 meters because the diameter is 6 meters. The pressure at depth z at each point on the semicircle is pressure as a function of z equals the density of water times g times z. And it's always normal to the surface of the tunnel. To find wrx and wry, we need to be able to express pressure as a function of arc length instead of pressure as a function of z. So we need this one and not this one. For that, we have to express z as a function of arc length, because then you will have pressure as a function of z, but z itself is written as a function of arc length. If you take a point on top of a tunnel at some kind of c, at some kind of arc length, then its vertical distance till the bottom is CV. That CV equals r times sine theta. And now, for example, if we say that this is our CV and the total depth from the surface of the sea till the bottom is 9 meters, then it makes sense if you write that z equals 9 minus CV. This z here, you get it when you take 9 and from it you subtract CV. If CV equals 0 meters, then z equals 9 minus 0 equals 9 meters, because there is no CV here. If CV equals 3 meters, then z equals 9 minus 3 equals 6 meters. That's when you are here. That's when your CV equals your radius. But you know that your CV is r times sine theta. So z equals 9 minus r times sine theta. Now note that the arc C can be calculated like this, r times theta, where theta is in radians, by the way. In here, theta must be in radians and not in degrees. So that means that you can say that theta equals c over r. That means that in this equation here, you can replace this theta with c over r. So you have z equals 9 minus r times sine and then c over r. And now we take this equation where I have pressure as a function of z, and I'm gonna have pressure as a function of arc length equals rho v times g, and now instead of z, I will write this equation, 9 minus r times sine and then c over r. So that's your pressure as a function of arc length. And so now that we have our pressure as a function of arc length, if we now integrate this one here and this one here, in other words, we integrate this one from c equals 0 meters till c equals pi times r meters, and then we integrate this one from c equals 0 meters till c equals pi times r meters, well then of course you will get wrx and wry, but since you know that theta equals c over r and dc equals r times d theta, then instead of c over r here, I can have theta, and then in that case I will have pressure as a function of theta, which is rho w times g times 9 minus r times sine theta. And now these dc's here, they are written down like this, r times d theta and r times d theta. And then here I have pressure as a function of theta, and here as well. And now if I integrate that equation, then it will be integrated from theta equals 0 radians till theta equals pi radians. That's because you go from here up until here, 180 degrees. And then here as well, you go from theta equals 0 radians and pi radians. And now you have the ability to rewrite these integrals like this. One is this one, the other one is this one. Here you have cosine theta, and here you have sine theta. So you can see that your integrals are written only in terms of thetas. And now you have to solve for these integrals. And I'm going to use the Wolfram Alpha online integral calculator to do it. If I calculate these integrals, then my WRx, it will be 0 newtons over meter, and WRy, this number here, 391,054 newtons over meter. It makes sense that your WRx equals 0 newtons over meter. As you integrate these equations over the entire semicircle, all the horizontal components get cancelled out, and you're only left with a vertical component, WRY. And due to symmetry, you know that this WRY acts through the center of pressure per unit length on top of the tunnel along the tunnel length. So this WRY here, it's this one. Now this is one way to achieve this result. However, in the next video, I will show you an alternative method to achieve the same result. Thank you very much. Welcome back. I have a plate underwater that is curved. Let's call this depth H1 and this depth here H2, and since pressure is normal to the surface, you can see the fluid's pressure distribution on the inside of the plate. Of course, in reality, you have pressure on the plate from all sides. But let's just focus on one side, the inner side. If I ask you to find the total force per unit length, WR, due to this pressure on the inner side of the plate, where you know that this is your pressure distribution, so for example, here in this point, we can say that you have P1 equals rho g H1, that's in this point, because this is your depth, and then in this location, you have P2 equals rho g times H2, so that's this point here, because this is your depth, and here it's in pascals or newtons over meter squared. Then you can get your WR through integration just like before. And then instead of this pressure, you will have some kind of pressure per unit length of this plate that goes along the length of the plate. Now you can do it through integration, or you can use another trick that will give you the same result. You can take this curved plate and you can separate a block of water directly above it. Now the water above this selected block exerts pressure on it. The pressure is uniform because the depth of the horizontal side of this block of water does not change. So in this case, it would be rho g times H1. However, the pressure on this block from the side does change, but it changes linearly with depth. So for example, here you have pressure equals rho g H1, that's this side, and then here you have pressure equals rho g H2, which is this side, but now the change is linear. Finally, the chunk of water that we have isolated, it has mass, and therefore it also has force of gravity per unit length that we can call Wg, and it's newtons over meter, and it goes through the center of gravity of this block of water. Now, since the density of water is constant, and also the gravitational acceleration is constant, the Cg, it's also our Cm and our centroid. Now, the mass per unit length of this isolated chunk of water is ml equals the density of water times the area of this isolated chunk of water. So ml, it's in kilograms over meter, rho v, it's in kilograms per cube meter, then area, it's in meters squared, and so of course you will have kilograms over meter. Then the density of water, it's 1000 kilograms per cube meter, and that means that the gravity force per unit length, Wg, that's ml times g. In other words, it's rho w times a times g. And of course, it's newtons over meter. And now you can see that this block of water that we have separated in our minds, it experiences three things. It experiences horizontal pressure, it also experiences vertical pressure, and this WG. Since water, like other liquids, is nearly incompressible, due to Newton's third law, the plate itself experiences the same three components of pressure from water on the inner side of the plate. It means that if I integrate pH horizontally and PV vertically, and I also add WG into that mix, then I will get the same total WR that I would get through traditional integration. So I can get my WRX and WRY using this approach. In the end, of course, the resultant force would be WR. Even though you get the same WR like you would get with integration, I believe that it's easier to do because you break that complicated pressure distribution into easier parts that you can deal with individually. And so with that, let's go back to our tunnel exercise. And now the task is to use this new technique in order to find WRX and WRY for this tunnel. See if you get the same answers like before. Remember, WRX, it was 0 newtons over meter, and WRY, it was this one. These are the answers that you got using integration. But now, let's see if you get the same numbers using this easier approach. Try doing it on your own first, and then see the solutions in the next video. Thank you very much. Welcome back. Let's now find the pressure force per unit length using the alternative method. We have our semicircular tunnel. Let's identify two sections or pockets of water, one on the left and one on the right. Just like in the previous video, the water column above that rectangular block creates uniform downward pressure distribution. Let's call it pH. It equals the water density times G times 6, because as you know, the depth of this location is 6 meters. The radius is 3 meters, the total depth is 9 meters, 9 minus 3 will give you 6 meters. On the sides you have two equal pressure distributions that are opposite to each other, and therefore you can see that they simply cancel each other out. Because of that, you already know that WRX, it equals 0 newtons over meter, because this side is cancelled out by this side. And then you have two side pockets of water with areas A1 and A2. These two pockets of water have force of gravities per unit length. They pass through their respective center of gravities. So the pocket of water on the left has some kind of center of gravity, and the one on the right also has some kind of center of gravity. Normally, we would have to calculate the locations of those center of gravities, but in this case, it's not necessary. Both center of gravities of these two pockets of water are at an equal distance from this vertical axis, and they are on opposite sides. So you know that if you add up WG1 and WG2, then this sum will act along this vertical axis. Also, your horizontal pressure, if you multiply it by the diameter of the semicircle, which is 6 meters, then that resultant force per unit length, which we can call WH, it will also act through the same location. So if you add them all together, then you will get your WRY, and that's WG1 plus WG2 plus pH times 6. And it will all act through this point. And so let's find it. First of all, pH times 6, that's rho g 6 times 6. You have this 6 here because that's the depth of this uniform horizontal pressure distribution. And then this 6 here, that's the diameter of the semicircle. So you have 1000 times g times 6 squared. That's 36,000 g newtons over meter. Then the area of the entire rectangle that contains both the semicircle and the 2 pockets of water, it's 6 times 3 equals 18 square meters. Then the area of the semicircle itself, well, that's pi r squared, which is the area of a circle, divided by 2. So you have 3 squared times pi over 2. And that's 9 pi over 2 meters squared. That means the total area of these 2 pockets of water, A1 plus A2, well, that's the area of the rectangle minus the area of the semicircle. So that's going to be 18 minus 9 pi over 2 meters squared. That means that WG1 plus WG2, these two guys, you have the mass per unit length for the first pocket of water times G. The same thing for the second pocket of water. You can rewrite it all like this, or also like this, and you know what your A1 plus A2 is. It's this one here, and you know the density of water, 1000 kilograms per cube meter. So it's gonna be 1000 G times all this, newtons over meter. That means that WRY equals 36,000 G, which is this one here, plus all this, which is this one here. And if you add it all together, you get 391,054 newtons over meter. And look, the same answer that you had before when you used integration. However, this method is much easier. Wouldn't you agree? Thank you very much.